All right, good evening, everyone, and welcome to this general members meeting of the Sacramento Valley Astronomical Society. I'm Vice President Raj Dixit. Our illustrious speaker tonight is Mr. Stephen Flanders of Caltech.
Illustrious.
Yes. Mr. Stephen Flanders of Caltech and of Palomar Observatory. He's the events coordinator, and he will be lecturing tonight and presenting on the history of the science that has been and continues to be done at Palomar from its inception through to the present day. So, Mr. Flanders, thank you so much for joining us, and the presentation is yours.
Raj, thank you very much, and thank you to everybody for being here. It's good to meet everyone, and thank you for asking me to speak to you tonight. Let me share my screen, and we'll get started with the presentation. And can everybody see that?
Looks to be coming through quite clearly.
Excellent. Okay. Hey, my name's Steve Flanders, and I work for Caltech, and I run the public outreach program at Palomar Observatory. I'd like to spend a little time tonight talking about the science and engineering at the observatory, and I hope you'll find it a pretty impressive story. We were talking earlier, and I think a number of us have had very similar experiences. In the 1950s, when I was getting in, late 1950s, when I was getting interested in astronomy, this was a very important and very famous place. It was a cultural icon at the time. Well, it's not so famous anymore, but Palomar Observatory remains an important and productive contributor to the global scientific enterprise. I'd like to organize this presentation around three topics. First, our mission of the observatory. Second, an overview of the facilities that support our science operations. And third, a summary of what we've achieved over the last 86 years, what contributions we have made to science over the last 86 years. Palomar Observatory is owned and operated by the California Institute of Technology. Excuse me. These are the 4 points of our mission statement. We support the work of professional astronomers. We train students at the graduate level. We engineer new science instruments, and we share our results with the public. Well, as you read these lines, please understand that this mission statement is aspirational in nature and does not necessarily describe what we actually do. What we actually do can be described very simply. We convert starlight into data. We do so very efficiently and very reliably. On the Hale Telescope, we maintain a suite of science instruments, imagers, spectrographs, photometers, and others, for the use of the astronomers. At an observing run, they use one or more of the science instruments to collect the data they need for their research. The data produced by the science instruments is our product, and the astronomers are our customers. Their home institutions pay a fee for each night of observing. Well, the facilities of the observatory World-class science is being done at Palomar Observatory, and a certain infrastructure is needed to support that science program. In this section, we'll look at the property, at the telescopes, and at the current inventory of science instruments. These things are our tools of science. Palomar's science enterprise started in 1936 when an 8-inch Schmidt wide-field telescope went into service on the mountain. This dome, the dome that housed the 18-inch telescope, stands a quarter of a mile east of the dome of the Hale Telescope. Here's an overview of the observatory's property on Palomar Mountain in northern San Diego County, California. We are looking to the southeast across a plateau that lies at an elevation of 5,600 feet and encompasses the 2,200 acres that Caltech owns up here. San Diego is almost directly behind the position of the camera and 50 miles away. Los Angeles is also behind the camera, but more to the left side of the frame. LA is about 90 miles away. Let me label and describe each of the domes that you see in this picture. Here we see the location of the dome that we saw in that previous slide just a moment ago. It once housed the 18-inch telescope that Fritz Zwicky used in the 1930s to search for supernovae. The instrument was decommissioned in 1999 and is now on display in the observatory's museum. The dome now houses weather instruments. The designation P18 is the shorthand we use when referring to the domes and the telescopes. The Palomar Cattini IR near-infrared survey telescope is housed in a small structure located behind P18. In this view, the building is obscured by trees. Although Cattini IR houses a 30-centimeter telescope, the building in which it is mounted once housed a 20-inch telescope. So, since we have long memories up here, the building and the telescope retain the label P20. On the left is the dome of the 48-inch Samuel Ocean wide-field Schmidt telescope. Brought into service in 1948, this telescope was used to conduct the two Palomar Sky surveys, the first in the 1950s, the second in the 1980s. It now supports an optical all-sky transient survey named the Zwicky Transient Facility, or ZTF. This is the observatory's Discovery Telescope, and in the last section of this presentation, we'll talk about its role in ZTF. To the far right is the Palomar 60-inch telescope. It was built to take some of the observing load off of the Hale Telescope and was commissioned in 1970. P60, as it is called, now operates robotically as part of the ZTF system, where it uses a low-resolution spectrograph to automatically categorize discoveries made by the 48-inch telescope. P60 uses a Ritchie-Chrétien optical configuration. The 200-inch Hale Telescope began science operations in 1949. It remained the largest effective telescope in the world until the first of the 10-meter Keck telescopes went into service in 1993. The 1-meter Winter Telescope is located several hundred yards west of P200. A recent addition, its dome was not in place when this image was taken. Winter is a robotic near-infrared synoptic survey telescope. Winter and Palomar Gattini IR have complementary but slightly different objectives we'll talk about a little later. To summarize, there are 5 active telescopes on the mountain, 2 optical survey telescopes, 2 near-infrared survey telescopes, and 1 general-purpose research telescope. The 4 survey telescopes operate robotically and are Q-scheduled. Top row, beginning from the left, is the 48-inch Samuel Ocean Schmidt telescope, and next to it, the 60-inch telescope. Both are now dedicated entirely to ZTF. On the second row, we see the 30-centimeter Gattini IR telescope, and next to it, the 1-meter Winter telescope. Both observe at near-infrared wavelengths. Winter is a plane wave telescope with a custom camera made by MIT. We refer to these 4 instruments as our discovery telescopes because their function is to repeatedly image the sky and find things that either have changed or have not been seen before or are different in any way, what we refer to under the term transients. Then finally, there's the 200-inch Hale Telescope, and it is used for spectroscopy, photometry, and imaging at visible and near-infrared wavelengths. The instruments used for imaging and photometry are mounted at prime focus at the top of the tube. Prime focus is an f3.3 modified Newtonian optical system. Spectroscopy is done at Cassegrain focus, an f16 system at the bottom of the tube. Our adaptive optics system is installed at Cassegrain focus. Observing nights are assigned to astronomers by a time allocation committee. Time on the telescope is granted to professional astronomers and graduate students who are conducting original research projects. In service for 73 years, this is the last major astronomical telescope to use a thick single-piece mirror cast from 14.5 tons of borosilicate glass, or Pyrex as it was known then. The mirror is not rigid. Instead, its shape is maintained by 36 mechanical levers that support the mirror from behind. This is also the largest telescope ever built on an equatorial mounting. No larger equatorially mounted telescope was ever constructed due to weight limitations. In fact, the moving parts of the telescope seen here weigh 530 tons. All of today's larger telescopes are mounted in azimuth. The telescope turns in right ascension on high-pressure oil bearings. The oil system was a major innovation in the 1930s, and still today, it allows the telescope to turn with so little friction that until very recently, its motion in right ascension was driven by a 1/12 horsepower motor. What follows then is a list of the 9 science instruments astronomers may use when observing on the Hale Telescope. These 9 instruments are grouped into 3 categories with 3 instruments each. First, 3 seeing limited instruments installed at prime focus. Second, 3 seeing limited instruments installed at Cassegrain focus. And third, 3 diffraction limited instruments installed at Cassegrain focus. The 3 seeing limited instruments used at prime focus. First, the wafer scale imager for prime, or WASP, is a visible light imager. The wide field infrared camera polarimeter, or WORK-POL, is a near infrared spectropolarimeter, and Chimera is a high-speed imager photometer. The 3 seeing limited instruments at Cassegrain focus are first, the Cosmic Web Imager, or CWI, is a multi-wavelength integral field imaging spectrograph that came to Palomar as a prototype used in the development of a similar instrument for the 10-meter Keck telescopes. Second, double spec is our most frequently used instrument, a single object visible light spectrograph that has been on the telescope for 12 years and will soon be upgraded by the next generation Palomar spectrograph now in development. And third, triple spec is used at near infrared wavelengths for single object spectroscopy. And it is doing so at a time when it is taking an ever larger role at the observatory due to the progressive brightening of our skies. And third category, the diffraction limited instruments at Cassegrain focus are first, PALM 3000, the observatory's adaptive optics system. PALM 3000 presently supports 2 instruments. First, the Palomar High Angular Resolution Observer, or FARO, is a near-infrared imaging spectrometer. And the second instrument, Palomar Radial Velocity Instrument, or PARVI, is a high-resolution infrared spectrograph and coronagraph used for precision radial velocity studies. Under favorable conditions, PALM 3000 allows these 2 instruments to operate at nearly the Hale Telescope's theoretical diffraction limit of 0.0565 seconds of arc at 1140 nanometers wavelength. Well, these telescopes and these instruments are the tools that make it possible for us to do world-class science. With that in mind, let's go on to the third section of the presentation, and let me draw up an account of our contributions to the science of astronomy over the past 9 decades. I'll summarize this broad topic under 6 general headings. These are the 6 research subject areas that, over the years, astronomers have been most concerned with. Probably Palomar Observatory's greatest contributions have been made in these areas, And these subjects continue to dominate the work that goes on here. I'd like to touch upon each of these areas in order, but first, well, I need to stop and point to what may be obvious, not sure. These things talk about discoveries and the people who made them. These things always have more actors and more complications than can be addressed in a short discussion like this. The goal of this presentation is to describe the roles that Palomar astronomers played in some of the most important advances in astrophysics of the last 7 or more decades. To do this, many details must be ignored, and the work of many contributors must go unmentioned. This is especially true in the much abbreviated discussion of the work of Edwin Hubble that follows. But let's begin with a bit of historical context. Many of Palomar Observatory's early science programs were continuations of work initially undertaken at Mount Wilson Observatory, home of the world's largest telescope in the years before operations began on the 200-inch Hale Telescope. And Edwin Hubble used the 100-inch telescope. You can see the dome of the Hooker telescope there on the left in this modern image. Well, one of the most important of Palomar's early science programs was built upon Edwin Hubble's discoveries at Mount Wilson in the 1920s. Two key items. First, he discovered that the universe contained not one, but millions or billions of galaxies. And second, he discovered that with only a few exceptions, every galaxy we could see was moving away from us at a rate proportional to its distance. Well, probably a familiar story to most of us, Hubble's discovery of the expansion of the universe set off a race to determine the rate at which the universe was expanding. For a variety of reasons, Hubble was never able to arrive at a generally accepted value for the rate of cosmic expansion, what we now refer to as the Hubble constant. His estimates predicated a young and a small universe that contradicted ideas then accepted by experts in other fields. Famously, at one point, he postulated a universe that was younger than the things it contained. Well, as a result, that question was open, and with the start of science operations in November 1949, the problem of determining the rate of cosmic expansion passed to Palomar Observatory and to the Hale Telescope. Observing at Mount Wilson and later at Palomar, Walter Baade took up this problem. He found two distinct populations of variable stars in the Andromeda Galaxy. From this discovery in 1953, he produced a revised estimate of the expansion rate that doubled our understanding of the size of the universe. Even so, contradictions in the data remain, and investigations by others continue. Finally, in the late 1950s, observing with the Hale Telescope, Caltech astronomer Alan Sandage made his own calculation of the expansion rate and published a value for the Hubble constant of 75 kilometers per second per megaparsec. His estimate is consistent with recent values obtained using the Hubble Space Telescope and other ground-based telescopes. Which is to say, to a close approximation, at Palomar Observatory, we correctly determined the age and size of the universe. This is often cited as representing our first and most significant contribution to science. Well, of course, I think we know why that number is so important. To put the matter simply, the expansion rate is important because everything we know about the universe beyond our own galaxy depends upon knowing speed and distance. The adoption of a generally accepted value for the Hubble constant made it possible to use redshift as an indicator of absolute distance and of chronological age. As this diagram may suggest, the Hubble constant underlies and enables many subsequent discoveries. And let me illustrate that relationship. Let me cite as an example a case from Palomar's science programs in which a later discovery was dependent upon Alan Sandage's findings and his calculation of the Hubble constant. This brings us to the high energy universe. Among the many extraordinary discoveries in the distant universe facilitated by the Hale Telescope, one of the most important was the identification of the radio loud source 3C273 by Martin Schmidt, Alan Sandage, and collaborators in 1963. Schmidt knew this object lay at a great distance because he could see that the lines in its spectrum were strongly redshifted. In fact, using the value Sandage had obtained for the Hubble constant, Schmidt calculated that 3C273 was 2.5 billion light years away, at the time, one of the most distant objects ever seen. But this distance meant that its intrinsic luminosity was hundreds, maybe thousands of times that of the Milky Way. No known physical process was thought to be capable of producing such a vast energy output. In this instance, the value of the Hubble constant was of critical importance for two contrasting reasons. First, Schmidt's discovery was entirely dependent on the value for the Hubble constant Sandage had derived. Had Schmidt used, for example, one of the values Edwin Hubble had published years earlier, Schmidt could have looked at 3C273's spectrum and concluded that because it seemed to be relatively close, again, in Edwin Hubble's small and young universe, it seemed to be relatively close, and its luminosity could be accounted for by known physical mechanisms. Only in the much larger and much older universe modeled by Sandage did the extraordinary character of this object become strikingly apparent. This example shows why Sandage's publication of a correct as we now understand, value for the Hubble constant was of such great importance to the advance of cosmology and to science in general. But if Schmidt's discovery was dependent on Sandage's earlier work, then it is also true that a great many later discoveries were dependent upon the work Schmidt had done. In particular, Schmidt's discovery raised important new questions that set astronomers around the world hurrying to find the source of 3C 273's power. Eventually, they realized that this and other similar objects lay at the center of galaxies, and soon their research led to black holes and to the idea that the enormous energy output of these galaxies was generated by the accretion of gas and dust around black holes at their centers. Eventually, researchers would confirm the presence of supermassive black holes in the nuclei of virtually every large galaxy, an idea recently demonstrated in images taken by the Event Horizon Telescope. All of which is to say, at Palomar Observatory, we opened the door to investigations of the high-energy universe. We count this as our second major contribution to science. Well, looking at these discoveries, it is clear that spectroscopy was and still is the essential technology that enabled the work of Sandage and Schmidt and many others. In fact, the analysis of the spectra of astronomical objects is the most powerful tool we have for understanding physical processes at work in the universe. Spectroscopy is indispensable to the science of astrophysics. And once it was established that the universe had a beginning, spectroscopy was used to determine its chemical composition, and at Palomar to demonstrate that this composition had evolved and grown more complex over time. Well, Caltech astronomer Jesse Greenstein, it seemed obvious that the universe had become chemically more complex. Ideas about the Big Bang gave him reason to believe that the universe had started out with a very simple set of elements. From this premise, he could prove that sometime between the simple beginnings and the present day, a great elaboration had taken place in the chemical complexity of the universe. Working on the Hale Telescope, he constructed his proof by analyzing the spectra of hundreds of stars near us in the Milky Way. The result was a catalog that enumerated and measured the chemical abundances of our galaxy and, by extension, of the universe. Well, soon his work led to a scientific collaboration with nuclear physicist Willie Fowler, and it was Fowler, together with Fred Hoyle and Margaret and Godfrey Burbidge, who solved the puzzle of how stars synthesize heavy elements from lighter ones in nuclear reactions in their cores. In 1983, Fowler received a Nobel Prize in Physics for his theory of nucleosynthesis. At Palomar, we consider our participation and our contributions to the development of this theory of nucleosynthesis our third major scientific contribution. And I should point out that these things all continue. Palomar continues to play a role in the exploration of the chemical universe. Caltech's LIGO observatories have recently observed gravitational waves produced by neutron star mergers. The 48-inch Samuel Ocean Telescope then has helped locate the afterglows produced by these events, glows that we now call kilonova. And the spectrographs on the Hale Telescope have helped analyze their compositions. Well, this work has closed a gap in the theory of nucleosynthesis. Indeed, the theory put forward by Fowler and others could not account for the creation of the heaviest elements. They knew that the heaviest elements must originate not in the cores of dying stars, but in unknown and unseen processes capable of generating much greater energies. Such processes were talked about by theorists, but Fowler and his colleagues had no observational evidence. Of course, we now have the evidence. Spectrographic analysis of kilonova seen after recent gravitational wave events has confirmed that gold and platinum and other heavy elements are synthesized in the merger of neutron stars. And this knowledge has, of course, been enabled by advances in technology that have come out of Caltech and other institutions. Well, technological innovation has been part of Caltech's reason for being, if you will, right from the beginning. Palomar Observatory's services continue to be in demand in part because Caltech is committed to the design and engineering of the world's most advanced science instruments. Often the development and prototyping of new devices is done on the Hale Telescope. As a result, Palomar astronomers always have access to the latest technology. A tradition of innovation and technical excellence runs through the history of the telescope. And the telescope itself embodies dozens of technological innovations in its design and construction. And here we see an example. Caltech developed a process of vacuum deposition that enables us to put a very thin coating of reflective aluminum on a glass surface. This was developed in the 1930s as they were building the telescope, first tested at Mount Wilson. Before that, they used silver. And that was one of the innovations that we came up with here and was done on the telescope. And of course, the list of technical innovations is long. The first electronic detector for astronomy, a pulse counting photometer, was installed on the 200-inch telescope in the 1950s. Computers for telescope control and data acquisition were introduced in the 1970s. Toward the end of that decade, Jim Gunn and James Westphal developed a camera they called 4-shooter. It used 4 800 by 800 CCD chips, and on the 200-inch telescope was able to reach magnitude 24 in 60 seconds. 4-shooter, now in the Smithsonian Institution, was a fully functional astronomical instrument that at the same time served as a prototype for the Hubble Space Telescope's wide-field planetary camera. And in addition to these sorts of things, we have also been at the forefront in the development of adaptive optics. Our first adaptive optic device was commissioned in December 1999. In fact, using the AO systems that have been developed on the Hale Telescope, we are able to image exoplanets directly by attaching an imaging spectrograph and a coronagraph to Palm 3000, and by taking a sequence of images at increasing wavelengths, we are able to know what an exoplanet, or at least its atmosphere, is made of. And, well, I think that's a pretty neat trick for an old telescope like this. And the adaptive optics is one of several methods and techniques we use to detect, image, and characterize exoplanets and brown dwarf stars. Here's a list of the methods and tools we use for exoplanet research, methods and tools that are also used in other areas, but these, I think these 6 items are key to how we study exoplanets. Astrometry measures shifts in a host star's position against the background. Photometry measures dimming during exoplanet transits. Spectroscopy, among other things, measures changes in a host star's radial velocity. Polarimetry isolates polarized light reflected from an exoplanet. The adaptive optic system corrects for atmospheric blurring and for errors in the optical system. And the coronagraph blocks the light of a host star. Our adaptive optic system has also been used for research involving objects much closer to home, that is, objects in our own solar system. Palomar Observatory has a tradition of discovering and studying the small objects that populate our solar system. These studies have resulted in a richer understanding of our solar system's architecture. A moment ago, we saw a view of Neptune taken with the adaptive optics system. Here, the Hale Telescope uses the same system to watch as Saturn's moon Titan occults a double star on December 20th, 2001. It's a remarkable bit of footage. Watch as the light from the stars is refracted around Titan's limb. Here you can see the light passing down under the limb of Titan. These refractions provided astronomers with information about the depth and density of Titan's atmosphere. Well, starting the same year, 2001, astronomer Mike Brown and his collaborators began discovering many small objects orbiting the sun beyond Neptune, what we now call the Kuiper Belt. His discovery of Eris prompted the International Astronomical Union to alter the meaning of the term planet in a way that removed Pluto from the roster of planets. The change necessitated the creation of a new designation, dwarf planet, as Pluto, Eris, and others are now classified. Mike Brown is proud of what he did. His Twitter name is Pluto Killer, and we feel ourselves complacent in the demotion of Pluto. Why we only now have 8 planets in our solar system. Well, astronomers at Palomar have observed our solar system as it changes and evolves. On March 24th, 1993, Carolyn Shoemaker discovered a comet, later named Comet Shoemaker-Levy 9, on photographic plates taken with the 18-inch telescope. Calculating its previous position, she realized that the object had recently passed close to Jupiter. And as it soon became clear, during that encounter, the comet had broken into a chain of fragments. Well, calculating then its orbit forward in time, she also realized that her comet would crash into Jupiter's atmosphere in July 1994, colliding with Jupiter's southern hemisphere on July 16th. The chain of fragments continued to fall into the cloud tops for 7 days. The event was viewed by professional and amateur astronomers around the world. The impact scars persisted for many months. And I should note here that we were aware of this event. We were able to look forward to this event and prepare for this event because Carolyn Shoemaker had been using the telescope to photograph the sky, to map its contents, and to look for transient objects. And this brings us to our last section, mapping the Palomar Sky. Our survey programs have been and continue to be the most broadly impactful scientific contribution made by Palomar Observatory. The 2 wide-field Schmidt telescopes, 48-inch Samuel Oschin telescopes, and until 1999, the 18-inch Schmidt telescope, have been the engines of discovery at the observatory since 1936. These telescopes have served this role because they have fields of view several hundred times that of the Hale Telescope. Now, the Samuel Oschin telescope has a survey camera that is able to reach magnitude 20.5 in 30 seconds and record 47 square degrees of sky on each exposure. This old 48-inch telescope is an ideal instrument for repeatedly imaging and mapping large portions of the sky. For years, we found comets and other things by doing photographic surveys. For almost 60 years, the 18-inch Schmidt was used for supernova searches and for mapping galaxy clusters, as well as for minor body detection. 6 major surveys were completed with this telescope before it was decommissioned in 1999. Of the 6, the Palomar Planet Crossing Asteroid Survey, which ran from 1973 to 1995, was probably the most influential and probably the most effective at raising awareness of the potential of asteroid collisions. During this period, Eleanor Helene and Jean and Carolyn Shoemaker discovered more than 100 near-Earth objects. Starting in 1948, the Samuel Oschin Telescope produced a series of astronomical surveys that remain scientifically important. Its first 5 decades of operation were dedicated to photographing and cataloging the entire visible sky from Palomar, as well as to conducting supernova searches and making stellar proper motion measurements. Currently, this telescope is dedicated to ZTF's program of repetitive imaging. The system has detected hundreds of transient objects. variable stars, flares, novae and supernovae of all types, excuse me, gamma ray bursters, AGN eruptions, and a variety of other phenomena. Operating robotically, the 48 inches of the Discovery Telescope for the Zwicky Transient Facility and for the observatory. And finally, Palomar Gattini IR has been in operation for several years. Its job is to take wide field images that are used to create catalogs of objects in the near infrared sky. No, excuse me, no such inventory has ever existed before. And now this telescope is finding nebulae and other objects that have never been seen at visible wavelengths. Commissioning of the Winter Telescope is almost complete, and soon it will begin a synoptic survey of near-infrared transients using technologies similar to those used with the 48-inch Samuel Ocean Telescope in ZTF. And with that, we've looked at the telescopes, we've described their individual roles, and listed the Hale Telescope's specialized science instruments. Then we divided the science of Palomar Observatory into 6 subject areas and discussed at least some of the contributions and advancements that have been made. And with that, George Ellery Hale had a motto. George Ellery Hale was the founder of all this. He said, "Make no small plans, dream no small dreams." And I think Palomar Observatory kind of embodies that motto. Hey, thank you much. And I hope we have some questions and discussions. And I'd love to talk about all this for a while. Thank you.